Hello and welcome back to PC Retro Programmer. Today's video is about rotating objects on the screen using an algorithm called CORDIC, which stands for Coordinate Rotation Digital Computer, which is a pretty cool name if you ask me. Now I appreciate that not everyone remembers trigonometry from their high school days, and so I'm going to go through that fairly carefully. And far from there being a negative association with math here, there are parts of retro computing where it's really just a passport to fun. So it's really worth looking at this stuff. Now, we don't need very much today, just some very basic trig definitions, enough to allow us to do vector rotation, which said another way is rotations of points about a common origin. Now, some viewers may not even recall the definition of the sine and cosine functions, the two main functions that we deal with in trigonometry, or they may have been taught them in a way that's not really applicable to what we're doing today. So let me start with the definitions, which turn out to be really quite straightforward. Now, suppose that you have a circle and it's centered at the origin and it has radius 1. So we call this the unit circle. Every point on this circle is distance 1 from the origin. So for example, this would be point 1, 0, this would be 0, 1, and so on. Now it turns out that on the unit circle, the coordinates of points on this circle are actually given by the cosine and sine functions. So for example, this point here would have coordinates cosine theta, sine theta, where theta is the angle that you make with respect to the x-axis. So the angles are always taken counterclockwise and they always start at the x-axis. So basically, if you have a pocket calculator, you just plug in this angle here and compute cosine theta and sine theta, and those would be the coordinates of the point on the unit circle. Now obviously I'm talking about real numbers here. The values that we've got range from -1 to 1 in the x case and -1 to 1 in the y case. And so these are real numbers. If you wanted to plot points on a computer screen where you have integer coordinates, you're going to have to scale this diagram up. For example, if you had a circle of radius r, you're going to have to multiply everything by r. And so in that case, the coordinates would be r times cosine theta, r times sine theta. And obviously to get integer coordinates, you're going to have to round to the nearest integer when you take the coordinate values. But otherwise everything is exactly the same. In fact, you could plot a circle this way just by computing the cosine and sine functions, but that turns out to be a really dreadful way of plotting a circle. There are much better algorithms for that, and we've discussed those on the channel. But for rotations, cosine and sine are really important. Now when we think about angles, we typically think about there being 360 degrees in a circle. So the first quadrant we get 90 degrees to this point, then 180 to here, 270 to here, 360 to here. But mathematicians and also computers, as it turns out, don't use degrees to measure angles. There's a much better system for this called radians. And there's a couple of really important reasons why radians are better in this regard. So first of all, radians measure the distance along the arc to the point, along the circumference of the circle here. So this distance along this curved line is precisely the angle in radians, at least if you have a unit circle. And so because the circle has circumference 2 pi, if the radius is 1, then the number of radians around a circle is 2 pi. But otherwise it works exactly the same as degrees. It's just a different measurement system. And the second reason why radians are better is that if you have very small angles, then sine theta is very approximately equal to theta. So if you have an extremely small angle, you don't really need to compute this function. You just take theta itself, because it has almost exactly the same value as sine theta. And so that's a really useful approximation, which just doesn't work when you use degrees. Now what we want to do today is use these trig functions to rotate points about the origin. And you might have already noticed that if I start off with that rightmost point of the unit circle, that 1, 0, then if I rotate that anti-clockwise by an angle theta, I end up with coordinates precisely cos theta, sine theta, as we just saw. So there really is a link between these trig functions and rotation. And our aim today is to figure out how to rotate arbitrary points about the origin. Now, one other quantity we need is this function tan theta, which is just defined to be sine theta on cos theta. And I'm only using it for a notational convenience today. I just don't want to have to write sine divided by cos everywhere. So the gadget that we're actually going to use to rotate points about the origin, arbitrary points, is this thing here called a rotation matrix, corresponding to a rotation anticlockwise by this angle theta. And the way it works is that we start off with the point that we want to rotate in vector notation. There's nothing mysterious about that, it's just the coordinates of the point. So, for example, that point 1, 0, we just put 1 and 0 in here. And then I'm going to show you an equation which will allow us to compute the rotated point, in other words, this point rotated by the angle theta, anti-clockwise, and it's going to work for any point that we start with. It doesn't even need to be on the unit circle. And that's this equation here. So here is our original point that we started off with, and here is our rotation matrix R, which I've written out here. And the result of this computation, this matrix vector multiplication, which I need to explain, is precisely the rotated point. So it'll have coordinates xi plus 1 and yi plus 1, and they'll be the rotated coordinates. So let me explain this matrix vector multiplication. It's actually really straightforward. All you have to remember is row by column, row by column. So what do I mean by that? Well, the new x-coordinate, the rotated x-coordinate, is the top row by the column. So that turns out to be cos theta times xi minus sine theta times yi. And the new y-coordinate, yi plus 1, the rotated one, is this row by the column. So sine theta xi plus cos theta yi. So I could have just written those two formulae out, to be fair, but you might wonder why I would use this matrix vector notation and go through that explanation. Well, it could be that I have a whole bunch of rotations to do, and so each new rotation I want to do, I'd have to put the rotation matrix for it on the left here. And you could imagine that I could expand all of this out. I could start with the inside one here, the first rotation, expand that all out, that'll give me a new vector, then do the next rotation, that'll give me a new vector, and each of these is a matrix vector multiplication, and the result is going to be really messy, probably go over multiple pages. But whenever I write it in this notation using matrices, I can just look at one of these and read off, oh, that's a rotation by this angle theta in the counterclockwise direction. So it just makes things look a whole load neater. But yeah, the formula basically is rotated x-coordinate is cos theta times original x-coordinate minus sine theta times original y-coordinate, and the rotated y-coordinate is sine theta xi plus cos theta yi. So those are the rotation equations. Alright, so we come to CORDIC, and I'm not going to explain the whole algorithm because actually the main idea behind the algorithm is already enough to allow us to rotate points and is really cool on its own. So the first idea is to take out a factor cos theta from this matrix. So basically I'm going to pull out this factor k equals cos theta. I'm just going to pull it out the front of the matrix. And that'll mean I have to divide all of the entries in the matrix by k. So once you take out a factor, you divide by that factor through each of the entries. So let's do that. Cos theta divided by cos theta is 1. Minus sine theta divided by cos theta is minus tan theta. Remember, tan is just this quantity that we defined up here. Sine theta divided by cos theta is tan theta. And again, cos theta divided by cos theta is 1. So when we pull this factor cos theta out the front, this is the matrix we're left with. And it's simpler because it has two 1s in it. And so when we go to use this matrix, multiplication by 1 is trivial. So we've made things easier. Now we can actually do even better than this if we're prepared to do a little approximation. So it turns out that the tan function is a little bit like the sine function in that for very small values of theta, tan theta is approximately equal to theta. So I can actually even replace these with theta so long as I'm prepared to have a little bit of approximation. It's really very close for small values. And even if I don't want to have approximations and I want to work with exact values, there's a trick. And this is the next main trick behind CORDIC. The idea is that we just pick a value of theta which leads us to a really nice tan value. So I don't remember exactly what the value is, but it's somewhere around about 7 degrees. You end up with a tan value of exactly 1/8. And if I plug in some value somewhere around about 3.5 degrees, again, don't know the exact value, you end up with tan equal to 1/16. And you could do it for any value that you want to end up with here. And obviously multiplying by 1/8 or 1/16 is really trivial on a computer. It's just a bit shift. You just do a shift by 3 bits to the right if you want to multiply by 1/8, or 4 bits if you want to do 1/16. So we just literally pick the value of tan that we want and just put up with whatever rotation that corresponds to. And 7 degrees and 3.5 degrees, well, they're not too bad as rotations. If you just want to rotate an object on the screen and make it look okay and you want to do it really fast, that's what you're going to do. Now the only thing remaining is this constant k that we have to multiply by, and this I just have to work out on a pocket calculator. I'll figure out exactly what this theta value has to be, and I'll plug it into the cos function. I'll calculate this all on a pocket calculator and then hard code that constant k into my program. We're going to pick tan theta equals 1/8 or maybe 1/16, haven't decided yet. I'll work out this k by hand, and then we'll just hard code it in. And then finally, everything's really simple as far as multiplying by the matrix is concerned. It's just some additions, subtractions, and bit shifts. And this k value ends up only being multiplied, well, in the final analysis, it's really only multiplied by the final x and y coordinates. So there's only 2 multiplications by k, which is pretty low cost.